The following section discusses solution concentration. There are many ways to express the amount of solute dissolved in a solvent, which is what we would call concentration. Below are the concentration expressions that will be used in this course. Molarity, often given the symbol capital M, percent by mass, and mole fraction, symbolized by an X. In all cases, the more solute in a given amount of solution, the higher the concentration. Concentrated solutions have high concentrations, dilute solutions have low concentrations. Let's discuss molarity, symbolized by capital M. Two solutions can contain the same types of solute and solvent, but be quite different due to a difference in the proportion of the amounts of each. So we can have very concentrated salt water, like ocean water, like we talked about earlier, where those saltwater alligators can survive. And then we can have fresh water that has some salt in it, but is much, much less concentrated. Molarity is one way to measure the concentration of a solution, and it is given by the following equation. Molarity, capital M, is the moles of solute, so in our example, the moles of salt, per volume or divided by volume of solution in liters. So often we'll be talking about water, the volume of water in liters. Percent by mass, or mass percentage of a solute, is another way to measure concentration. It is commonly used on consumer products labels such as bleach. If the label indicates that the active ingredient in bleach is 7.4% sodium hypochlorite, that means that in 100 grams of bleach, there are 7.4 grams of sodium hypochlorite. Remember that a percent is a part per whole. So to calculate the percent by mass of a solute, any solute A, in our example, it would be sodium hypochlorite, you would take the mass of that solute in the solution divided by the total mass. That's how you find a percent, right? Part over whole, and then multiply by 100 to get your percentage. Finally, let's talk about mole fraction, represented by the letter X. Mole fraction is commonly used to describe mixtures of gases. This expression assumes that solute A is dissolved in solvent B. So when we're finding the mole fraction of A, we will take the moles of A, that moles of solute, divided by total moles. So moles of solute divided by total moles. Example 1, molarity. A solution contains 10 grams of silver nitrate in 300 milliliters of solution. What is the molarity of this solution? So as I've done in previous examples, I'm going to set this up here, and then we'll move forward to see the actual answer on the final slide. So starting with our question here, we're looking for molarity. So we need moles of solute, moles of AgNO3 over liters of solution. Okay, so we are not given moles, nor are we given liters. So we've got a little work to do here, right? So the first thing we need to do is convert this 10 grams of silver nitrate into moles. Silver nitrate has a molar mass of about 170 grams per mole. So that'll give us the moles of silver nitrate. And then we need to divide that by liters of solution. So 300 milliliters divided by 1,000 milliliters per liter will give us our liters. Okay, so 10 divided by 170 on the top and 300 divided by 1000 on the bottom. That would be 0.3. Okay, so I'm going to go ahead and go forward to the next slide and you can see the math done. So there's 10 divided by that approximately 170, so 0.0589 moles, and then 300 divided by 1000, 0.3 liters. And again, molarity is moles per liter. So we're just dividing 0.0589 moles by 0.300 liters to get 0.196 moles of AgNO3. So just for emphasis, this is the concentration in moles per liter. Here's a second example using molarity. An experiment calls for 250 milliliters of 0.5 molar NaOH. How many moles are being used? How many moles of NaOH are being used in this experiment? Okay, so I just want to point out some of the things we know. We have 0.50 molar NaOH. We have to remember that this is the same as 0.50 moles per liter of NaOH. Okay, and then we're told that we have 250 milliliters. So just as an aside, 250 milliliters is 0.250 liters. There's some more detail on the next slide of that conversion if you've forgotten it, right? But if we go with the math here, we say 0.50 moles per liter times 0.250 liters. That will give us our moles of NaOH. So 0.5 times 0.25 is 0.125 moles of NaOH. I'll move ahead to the next slide so that you can see the work and the answer. Here's our answer here rounded to, we got 0.125, right? Our answer here rounded to 2 significant figures. Example 3, mass percentage. A solution contains 15 grams of sodium chloride in 750 grams of water. What is the mass percent of sodium chloride in this solution? So remember that percent by mass of whatever we're looking for, which in this case is sodium chloride, would be the grams of sodium chloride over total grams. Okay, so the grams of sodium chloride is 15. The total grams is 15 plus 750 grams of water. And then of course, if we want this written as a percent, we would just say, let me move this here. We'll just say times 100. We do that, so 15 divided by 750 plus 15 is 765. It's 0.02. And then times 100 is about 2%. Okay, about 2%. So again, let's head to the next slide just to confirm. We can see here this confirmed 2% sodium chloride, just as our work showed. Example 4, mole fraction. A weather balloon contains 28.5 grams of hydrogen gas and 1.5 grams of helium gas. What is the mole fraction of helium in the weather balloon? Let's go to the next slide and walk through the answer. First, we need moles, right? Because we're finding mole fraction. So we're going to convert grams of hydrogen and grams of helium to moles. So hydrogen, remember, is not just H. Remember that hydrogen is H2. It's a diatomic H2. So if we have 28.5 grams of it, divide by the molar mass, which is approximately 2.016 grams per mole, we get 14.1 moles of hydrogen, H2. Helium is not diatomic, it's just He, so we can just go directly from the periodic table. 1.5 grams of this sample is helium, we're told. Divide by the molar mass, which is 4.003 grams per mole, to get 0.375 moles of helium. Once we know our moles, we're just finding how much of this sample, what fraction of this sample in moles is hydrogen. No. What is the mole fraction of helium? So we're going to take the moles of helium on the top, 0.375, and divide by the total number of moles, 14.1 plus 0.375, total number of moles, to get a mole fraction of 0.26. Notice this number is unitless because we have moles on the top and moles on the bottom. So those cancel, and we're just left with this fractional value of 0.26.